Hey guys, let me get rid of that. Okay, get rid of that. Sorry for a two-part video. I screwed up. I stopped the video before I did, hit publish, and here we are making part two. Anyway, we wanted to get into the idea of solubility and pH and how they interact with each other a little bit there. Up until now, when we've talked about our solutions, we've always been assuming that we're dissolving something in pure water, but we have to deal with the fact that water isn't always pure and what happens when there are other things in there. And so is it going to cause solubility to increase or decrease? You might automatically think, well, if there's stuff in there, then when I put stuff in, it won't dissolve as well. And that's true, but it also could work the other way. It could cause it to increase depending on what's going on with the ions. So let's talk about some scenarios. First, though, let's review solubility. So here's a question. What is the molar solubility of cadmium hydroxide in pure water at 25 degrees? KSP is 2.5 times 10 to the 14th. And then once you figure that out, we want to find the pH. So pause the video if you want, but I'm going to go on. So with KSP, we're always talking about dissociation of an ionic solid. So we're going to get cadmium hydroxide. We could assume they start at 0 because we're putting it in pure water. There's none of that stuff in there. The solubility is the change, even though it's a solid, we're talking about how much of that solid is going to dissolve. So that means that this would go up by S, this would go up by 2S. So we have our equilibrium values. KSP would be the products of reactants, but the reactant's a solid. So we have cadmium times hydroxide squared. We substitute in what we know. KSP is 2.5 times 10 to the 14th. Cadmium is S. Hydroxide is 2S, quantity squared. So I get 4S cubed. Divide by 4, take the cube root, the solubility dropping 1.84 times 10 to the 5th molars. Now, to find the pH, because this is a base, right, it's giving me hydroxide ions. If I can find the hydroxide, I can find the POH, and then I can find the pH. So hydroxide, we said, is 2S, so 2 times this gives me about 3.7 times 10 to the 5th. And if I take the negative log of that, I get 4.4, which means the pH would be 9.6. So that's the pure water. Now let's deal with the not so pure water. So let's assume we're going to redo the same problem, but now we're going to say, well, the water had a little bit of sodium hydroxide in it. What's that going to do? All right, so pause it if you want to give it a try yourself, but I'm going to go on. So the only change is now, because of the sodium hydroxide, we're going to say we're starting with hydroxide ions in there, about 0.01 molar. And so at equilibrium, we're going to have 0.01 plus 2S. But remember, this is a pretty weak, not very soluble salt, right? That KSP value is small. So 0.01 plus 2S is still going to be pretty much the same thing as just 0.01. So you notice here, I just wrote it as 0.01. I got rid of the 2S part. 0.01 squared is 1 times 10 to the 4th. So now I take 2.5 times 10 to the 14th, divide by 1 times 10 to the 4th, and that tells me my solubility now dropped dramatically to 2.5 times 10 to the 10th. All right, so again, it had been 1.84 times 10 to the 5th. Now it's down by almost 100,000 times, or actually, yeah, about 100,000 times. So big difference. Now, when we talk about the hydroxide, that 2S plus 0.01, well, that 2S is so small, it's all the 0.01. So the hydroxide is really all from the sodium hydroxide for the most part, which means the POH is 2 and the pH is 12. All right. So that was a mathematical approach. Let's talk about a conceptual approach here. So will the molar solubility of cadmium hydroxide increase, decrease, or remain the same in water that contains 0.01 molar HCl? Now, we just showed that when I tried to dissolve the base in a base, it decreases solubility. So, little logic, we're taking a base, dissolving it in an acid, not going to be the same answer. Okay, let's talk about why. So again, here's our reaction. Okay. We know that the hydrochloric acid is going to have hydronium ions present, and hydronium ions are going to neutralize hydroxide ions. There should be a 2 in there. That means that as soon as this reaction starts making hydroxides, this reaction is going to remove them, Remember Le Chatelier's principle. When you remove something, the reaction shifts to make more of it. So this reaction is going to shift to the right. It's going to make more hydroxide ions. Or we could talk about it in terms of reasoning. I didn't quote Le Chat. I could have. I talked about it in terms of Q. When I remove hydroxides, the value of Q is going to drop. So now it's going to be less than KSP, which means the reaction is going to move forward, okay, increasing the solubility. All right, so that's the idea of solubility and how it affects pH and whatnot, or how pH and solubility kind of interact there a bit. Now we're done. Bye.